In this lesson, we will learn to determine the limit of a polynomial function as x approaches a using some of the limit laws that we discussed in the previous lesson. And at the same time, we'll also learn about an important property called direct substitution property, which will make it further easier for us to determine the limit of a polynomial function. So let's take an example of a polynomial function. Suppose it is given by, say, 3x squared minus x plus 2. And let's say we have to determine the limit of this polynomial function 3x squared minus x plus 2 as x approaches minus 1. So in order to apply the limit laws here, we can take this function as composed of two functions. For example, the first is 3x squared minus x and the second is the constant function 2. So I can write this limit as x approaches minus 1 of 3x squared minus x plus limit as x approaches minus 1 of this constant function 2. So I have applied the limit law of addition here, which says that the limit of a sum is equal to the sum of the limits. And this is the first limit law that we discussed in our previous lesson. So in our list, it is at number 1. So I will write it as by law 1. Similarly, I can write this limit using the difference law. And according to which I will write this as limit as x approaches minus 1 of 3x squared minus limit as x approaches minus 1 of x. So the difference law says that the limit of a difference is equal to the difference of the limits. And in our list of limit laws, you can find it as law number 2. Now let's look at this limit. So 2 is a constant. So the limit of a constant is the constant itself. And we proved it in the previous lesson. So this limit will remain 2. And in our list of limit laws, it is at number 7. Again, I can write this limit as 3 times limit as x approaches minus 1 of x squared. And this is the law of constant multiple, which says that the limit of a constant times a function is equal to the constant times the limit. In our list in the previous lesson, it is at number 3. Now this limit is pretty straightforward. You can see as x approaches minus 1, the function itself is x, so it approaches minus 1. So this limit is minus 1. And if you remember, we had proved this result in our previous lessons. So this will be minus 1. And I'm writing 2 as it is for now. And in our list, this is at number 8. Now, again, this limit is pretty straightforward. As x approaches minus 1, it's intuitive that this x squared approaches minus 1 squared. So I can write this as 3 times minus 1 squared. And for now, I'm writing the rest of the digits as it is. And you will find it at number 9 in our list. So it is by 9. Now, if we quickly calculate it, it will come out to be 6. So the limit of this function as x approaches minus 1 comes out to be 6. So this is how we apply the limit laws in order to determine the limit of a function as x approaches a. And you could see that it's self-explanatory. Now I would like you to focus on this step right here. So what's so special about this step? So let me highlight this one. So see, isn't it the same step we would have obtained if we had substituted x is equal to minus 1 directly in this expression? So when you put x is equal to minus 1, in the first term of this expression, you will get 3 times minus 1 squared, and which is right here. And again, when you'll put x is equal to minus 1 here, you will get minus 1 times minus 1, and which is here, and this plus 2 is already here. And what do we get when we substitute x is equal to minus 1 in the expression of this function? it will give us the value of this function at x is equal to minus 1. So this is equal to the value of this function at x is equal to minus 1. So we've got an important result here. That is the limit of this function as x approaches minus 1 is equal to the value of this function at x is equal to minus 1. So this property, that is the limit of this function as x approaches minus 1 is equal to the value of this function at x is equal to minus 1, is called the direct substitution property. Because we can determine the limit of this function as x approaches minus 1 by directly substituting x is equal to minus 1 in the expression of this function. That is, just by determining the value of this function at x is equal to minus 1. Let's quickly look at it graphically. So for that, I have here the graph of this function which we just discussed, and you can see clearly that as x approaches minus 1, the points on the graph approach the point whose y-coordinate is equal to the value of this function at x is equal to minus 1. Now recall the meaning of the limit of a function as x approaches a. So the limit of a function as x approaches a is a number, which in this case is 6, to which the values of f approach as x approaches a. So which means that in this case, the value of f at x is equal to minus 1, which is 6, is also the limit of f as x approaches minus 1. That is why the limit of this function as x approaches minus 1 is equal to the value of this function at x is equal to minus 1. So this is the direct substitution property. And it is because of this property, we don't see a break in the graph at x is equal to minus 1. To make it clearer, I'm going to show you the graph of a function which is not a polynomial. So I have right here the graph of a function where you can see that as x approaches a, the points on the graph do not approach the point whose y-coordinate is equal to the value of this function at x is equal to a. That is, the limit of this function as x approaches a is not equal to the value of this function at x is equal to a. And it is because of this the graph is broken at x is equal to a, and which is not the case here. Now, have you ever seen the graph of a polynomial function with breaks in it? So, no. The graph of any polynomial function is free from breaks. And we'll learn more about the breaks in the graph of a function when we will deal with the topic of discontinuity of a function. So right now, let's focus on the graph of a polynomial function. So as I said that the graph of a polynomial function is free from breaks or holes, so which means that this property, that is the direct substitution property, is not just true for this particular point or for this particular polynomial function. The direct substitution property is true for any polynomial function in general on the entire set of real numbers. So if we talk about polynomial functions in general, you can see here, suppose a is any real number, whether x approaches a from the left or from the right side, in both the cases, the points on the graph approach the same point. That is, the values of the function approach the same number, which is the limit of a polynomial function. So I meant to say that the limit of a polynomial function as x approaches a always exists. And because a polynomial function is defined on the entire set of real numbers, so which means this f of a is defined. Now, on top of that, we see that the limit of a polynomial function as x approaches a is equal to the value of a polynomial function at x is equal to a. So that is, this limit is the same number as the value of this function at x is equal to a. So after this discussion, now we know that if f is a polynomial function and A belongs to the set of real numbers, which is also the domain of a polynomial function, then the limit of a polynomial function as x approaches a is equal to the value of f at x is equal to a. So this is the direct substitution property for polynomial functions. So now once we have learned this property, determining the limit of a polynomial function as x approaches a is not a big deal. So for example, if you have a function, say 9x cubed minus 6x squared plus x plus 1. And suppose you have to determine the limit of this function as x approaches minus 2. Now, we know that this is a polynomial function, so I can determine the limit of this polynomial function as x approaches minus 2 by applying the direct substitution property. That is by directly substituting x is equal to minus 2 in this expression, and which is the same as saying that determining the value of this function at x is equal to minus 2, and which will be 9 into minus 2 cube minus 6 times minus 2 square plus minus 2 plus 1, and which on simplification will give us minus 97. So we have determined the limit of this polynomial function as x approaches minus 2 without using the limit laws, just by applying the direct substitution property. Now in the next lesson, we will learn to determine the limit of a rational function as x approaches a.